Hi, good day everyone. So in this video, I'll be recording the tutorial for 25-29. So in the tutorial, we went through tutorial 15, the extra questions that were assigned, namely questions 13 and one question behind. And we also went to tutorial 17 to start sequences and series. Okay, so with this, let's start this tutorial. Now, let's go through the extra question on binomial and Maclaurin. Okay, so over here we want to find the expansion of this thing in ascending powers of x up to the x square term. So what we do is from the fraction we make the denominator into this form. Okay, by taking power negative half. And because we are expanding power negative half, which is not a positive integer, what we do is we'll do binomial expansion, but making use of the formula in the MF27. Okay, but before we expand, let's take note that we have to make the constant term a 1. And so we will factorize out 4 to the power of half, negative half, and we will get 1 minus x over 4. Okay, now then when we expand, the front part is like that. Then we make use of the formula to write in these terms. Okay, so namely all these, right, are actually sum of n choose r 1 to the power of r, sorry, here is actually n choose r 1 to the power of n minus r b to the power of r. Okay, or your x to the power of r. Okay, okay, and then this one over here is actually 1. Okay, because 1 to the power anything is 1. Okay, so we have all these things over here. Remember, this is n choose 0, right? N choose 0 is 1. N choose 1 is n choose 2 will be n minus 1 over 2 factorial. Okay, can now with this over here, we will expand, simplify, expand and simplify even further, and then simplify to our final answer. Okay, state part 2, state the set of values for x for which this expansion is valid. We will have to look where do we expand the binomial expression. So do we take anything from here? No need. There's no need to do x squared less than mod 1 because we did not expand this factor. Instead, we expanded this component over here, and this component we made use of the binomial expansion. So where do we look for the valid range of validity? From here, 1 plus something or 1 minus something. So this is the one will be modulus less than negative 1. Okay. The negative over there in the modulus is redundant. So we don't, yeah, technically we can ignore. Then over here we have negative 4 less than x less than 4. Okay. Now, hence, part 3, by substituting a suitable value of x, find an approximation for root 15 in the form a over b. So we want to write it in exact fractions. Okay. So what do we do over here, right, is that we will need to sub in x equals to something, right, into this expression over here, and we substitute x equals something into this expression over here, so that we can like do the calculation and to find our root 15. Okay, so it will be easy to think that we need to sub in negative 11. X is negative 11 because 4 minus negative 11, right, will be equals to 15. And because of here, we will get our root 15 already, right? But if we sub in negative 11, right, it will be outside the range of validity. So that means this cannot happen because it will make the approximation inaccurate. So instead, what we do is we have to find a smaller value within this range of validity to sub in. Okay, so what do we do? Okay, so a good number is actually 1 over 4 because 4 times 4 is 16. 16 minus 1 is 15. Okay, so we have to try our best to find 15 from whichever substitution that we put in. Okay, so the thing is we'll sub in 1 over 4, sub in 1 over 4, sub in 1 over 4. Okay, get something like this. Simplify. 6 and 2 will give us 8. Root 4, 6 and root 4, right? The 15 and root 15 will give us root 15 on top. Then you cross multiply the 8 to get there. Okay, so normally we don't reciprocate. Okay, if a root 15 is down there, what we do instead is to rationalize. Okay, so this one be careful. Okay, all right, so this would be what we have for question 13. Okay, next let's look at question 19, if I'm not mistaken. Okay, question 19. Okay, so for question 19 over here, this one is an exercise on Maclaurin series where we do repeated differentiation to get the Maclaurin series. Okay, so let's take a look. Part 1. Given that y is this function, find the exact range of values of x for y to be well defined. So this phrase over here, for y to be well defined, right? So this refers to the domain of the function. So what is the domain of the function such that the function exists? Okay, the function is well defined such that the function is possible. Okay, so we have to look at the functions over here. So what functions do we have? We have the square root function, we have the ln function, correct? So we need to analyze two things. Okay, we need to analyze two things. Okay, for this to exist, right, the ln content, right? For the ln content, the content itself must be positive for the ln function to exist. And because of that, the 1 plus x will be more than 0. Okay, next, we also want the content of the set, the square root, to be positive, okay, or at least 0. Okay, so that the function, we can process the value of the square root. So because of that, we have the content of the set more than 0. Okay, now, and so because of that, we solve, x will get this, x will get that. Now let's compare, because now we are solving, because it has to fulfill both requirement, right? So this is an and, not an or. We need to fulfill this and this inequality n. Okay, so because we are solving simultaneous linear inequality, we need to draw the number line to roughly see where is the common region. So negative 1 is here, 1 over e minus 1 is somewhere over here, right? If you were to think about it, okay, negative 1 plus 1 over e. So we have this region, we have this region, right? So where's the common region? The common region is actually over here. Okay, so because of this, the conclusion is x will be greater than 1 over e minus 1 for y to be well defined. Okay, so that it can fulfill both these criteria to fit the domain of the function. Okay, now part 2, show that this, okay, from y. So this is actually a clue to ask us to differentiate implicitly. Okay, of course you can do the direct differentiation, but it will take some time to massage it back to the original form. Okay, so the smart way to do is actually to square it. Okay, after squaring it, differentiate implicitly. Okay, now we need to replace this 1 plus x, right? So we need to find what is 1 plus x in terms of y. Okay, so we get something like this. Okay, and because of this, replace it, we will get everything in terms of y. Okay, then we will differentiate a few more times to find the Maclaurin series until x squared, right? So we need to just, x squared, then we differentiate one more time. Okay, so from here to here, this is a product rule. Okay, differentiate the y. So differentiate, copy, differentiate. Okay, then this one over here is chain rule. So differentiate e is e. Differentiate the power, we get something like this. Then differentiate the y, we get dy dx. So this is chain rule. Okay, this one be careful. This is a chain rule. Okay, so with this over here, simplify to get something like this. Okay, so now let's substitute. When x equals to 0, y equals to, sub in the 0. Sorry, apologies. This one sub in 0. Okay, so y equals to 1. Okay, then substituting y and x to find dy dx. Then substitute dy dx, right? Your y, okay, and x, okay. Then you evaluate your second derivative. So these numbers here will form your coefficients of your Maclaurin series. Okay, so y equals to 0 derivative over 0 factorial x power 0, first derivative over 1 factorial x power 1, second derivative over 2 factorial x power 2. So altogether, this is your Maclaurin expansion for y. Okay, Then the last one, the last part is verify that the same results is obtained using your standard series expansion given in the list of formula. Okay, so the first part, the first style is to find Maclaurin series by repeated differentiation. The second style, because this is a common function, so we can make use of standard results to find this fast. Okay, so what do we do first? Like to expand, we expand all the way from the inside. So let's settle the ln first. Okay, so expanding the ln, okay, expand until x squared, and then this is power half, right? So we do the binomial expansion. Okay, can also, I don't need to explain this too much because I just go through the approach. Okay, then we simplify, ignore higher terms, then we get the final answer over here. Then we just need to double check that both the expansions are equivalent. So theoretically speaking, two different approaches, but it's the same Maclaurin expansion. That's why it should be equivalent. Okay, so that's for tutorial 15, binomial and Maclaurin expansion.